Hello everyone, my name is Barış Akıncı. In this slide, I'm gonna talk about our Physics 2 class, Lab 3, which is about circuits. Introduction. Our goal is to verify circuit conservation laws using Kirchhoff's current law at junctions and Kirchhoff's voltage law around closed loops. We predict and measure currents and voltages in series and parallel resistors and study capacitor charging and discharging. Our purpose and principles. The purpose is verify current-voltage relations in a direct current loop, measure delta V across components and check sum of delta V's is equal to 0, capture capacitor charge and discharge and extract time constant which is equal to R times C. And the core principles are charge conservation of charge, conservation of energy, loop rule, and lastly, Ohm's law. Models and assumptions. So for our DC model first, ideal source, which is battery, ohmic resistors, and negligible wire drop. And for the RC model, where we're using the capacitor, the charging is VC T equals V battery minus V battery 1 minus e to the minus t over RC. And for discharging, same thing, but we're using V naught times e to the minus t over RC. And assumptions, we got constant R and C. Circuit and instrumentation. So we used battery, 47 ohms resistor and 100 ohms resistor, and then wires of course. And then we used the meters, ammeter in series and voltmeter in parallel. And the procedure was we moved the voltmeter across each element, know the sign and value. And these are our results for the first part of the experiment, which is DC. So for battery one, we measured the delta V is same for both batteries, and the sign is positive of course, and then I, the current, is 18.8 milliamperes for everywhere because it doesn't change. And then for the after resistors, measured V for the 47 ohm is 0.8 and 100 ohm was 1.8. And then of course when we add delta V's, we will get 0 with the negligible wire drop. So meter effects and equivalent to R. Voltmeter high R in, ammeter low R in, and from data R equals delta V over I, which give us for the 47 ohm resistor we got 42.6 ohms, and the 100 one we got 95.7 ohms. And quick note, the contact and wire resistance can explain small deviations that we had in the previous slide. So for our capacitor part of experiment setup and expectations, we use battery, resistor, capacitor, and switch. Expectations is lamp is bright and then dims, and for the finding the time constant, it's time equals R times C, and then larger R or C is slower charging and discharging. So this is our data, and how do we draw it? Method was we recorded the voltages after and before the resistors, and then we just put it on the linear graph. What if charge with no resistors? Ideal would be instantaneous charge, infinite spike current, but the real battery initial R, capacitor let's contact R, finite rise, limited peak, and then quick test would be measured charge in 10 seconds. Why different? Because non-ideal series R dominates when external, where R is equal to. So for the conclusion and checklist finally, the loop rule is verified, sum of delta V is equal to 0, the current is measured 18.8 and we predict 19.1, which is good. And then for the system and surroundings, system equals source, resistors, capacitor, and surroundings is meters, LEDs, and the environment. Main errors could be contact/wire R, matter solution, scale, probe, placement, and timing. Thank you for listening.